Hello, and welcome to the E3SM data regridding tutorial. My name is Tony Bartoletti, and I will be providing this walkthrough of the regridding guide written substantially by Sterling Baldwin. A copy of this guide should become available to you at the following URL. That would be highlighted here, e3sm.org/resources/documentation/how-to/regridding in good time. I will begin by discussing some topics common to anyone who might be using these tools, such as the required execution environment, the map files employed by the regridding operations, and offer a few words about regridding in general. I will also briefly survey my workspace to demonstrate a layout that allows me to minimize clutter as I conduct the tutorial and to familiarize you with that environment. Then, finally, depending upon which version of this tutorial you may be viewing, we will exercise regridding examples with either atmospheric, land, or the MPAS ocean data. So let's get started. I will come here to the PDF regridding guide on my left and scroll down to Chapter 1. And we talk about the environment setup. As the guide explains, you should first establish an Anaconda environment in which the necessary NCO tools are installed. If you already have a Conda environment you wish to use, you may add the NCO suite of tools with the first command indicated here under Conda. That would be Conda install -c Conda forge NCO. If instead you would like to create a Conda environment that's specific to doing the regridding and only contains the NCO tool suite, the second command should work for you. And as you see, it names a environment called Regrid, and I've used that one myself, and that's why if you look at my console window, my command prompt begins with the word regrid. There are also precompiled NCO tools available if you want to go that route. And the URL is up here under the NCO documentation. So at this point, I'd like to talk about regridding in general. Why do we do regridding in the first place? Turns out that, of course, many simulation models exist, and they produce data on different grid types and with different resolutions. In order to conduct side-by-side comparison between simulations or to combine simulation data in conducting forms of secondary analysis, the output must be presented on the same grid. If you have data on two different grids, you will need to convert the data of one into the grid of the other in order to compare or combine them. There are many regridding methods, but the most common are the area averaged and the bilinear methods, which I will describe briefly here. The area averaged method is employed when you are moving from a high resolution grid, the destination, or the source grid here indicated in red, and you want to convert the data into a lower resolution destination grid with larger cells indicated in blue here. The value that you're going to want to obtain for each blue cell is going to come from a variety of smaller source cells, and it will be the cells that are covered by the blue cell, either entirely or in some portion. And the contribution of the source cells corresponds to the fraction of those cells that are covered. So we see here that there will be 4 cells, source cells, that will contribute 100% of their value, or along the periphery we see that there are other source cells that will only contribute a smaller weight of their value, and that weighted average is what is assigned to the destination cell. In contrast, when moving from a coarse resolution, large cells, in this case the red source grid, to a grid that's of finer resolution, the blue destination grid, we consider that each source grid cell, imagine its values to be concentrated at its center, represented by its center point. And then every blue cell that happens to find these four cells, source cells, to be the closest ones, will have its center fall within the bounding box connecting the centers of the source cells. And that each blue cell then is going to receive some value from the four source cells, but in proportion corresponding to how close the center of the blue cell is to those red centers. So we can see in this case that the point P at the center of this destination blue cell will be receiving more weight from the value in this large red cell B than and the least from this one over C over at this end, which is further away. So that is pretty much what I'm going to describe about regridding methods. Now, because there exists a wealth of standard Earth-spanning grids already, regridding is facilitated by map files that are pre-configured to conduct the cell-by-cell weighting of cell contribution from a known grid, source grid, to a known destination grid. These map files are available at this Argonne National Laboratory site. There are scores of them. We won't have to pull those down because I've already got several of them on hand. As you can see here in my console window, there are scores of different source to destination grid transformations that are already available. We will only be using a few of these, of course, in the tutorial. So I might also add that the data that you might want to examine or regrid, there is a wealth of that data, E3SM data published, a wealth of climate model simulation data available at the ESGF ESGF node website here, with a search front end that will allow you to select data sets from different experiments according to a variety of different criteria. I've already downloaded and have available a variety of data that we'll be using for some regridding here. So before I go any further, I'd like to introduce my environment. You see, in my environment is divided into a variety of source directories that are already populated with data for these tutorials, and I will demonstrate these by just looking at a few files from each one. See, we have two directories of atmospheric model data, two of land model data, and two directories of the MPAS ocean data. And you'll be seeing some of that data depending on which video you may be viewing here. So likewise, once the regridding occurs, the output will end up in these different destination directories at the top. There, we can see that they're actually empty by replacing source with dest here, and there's nothing in these directories yet, but they will be populated as the example grid runs occur. So with that, I think it's probably time to launch into the actual regridding examples. All right, so for this version of the tutorial, we will examine Chapter 3 of the guide, Land Regridding. We will have 4 different examples to explore. The source data is going to come from these 2 directories I will highlight here. They are the source for the land model data, monthly averages. The one directory, the shorter name, has all the files from 1850 through the year 2014. The second directory only has the single year 1850. That's all that's required for some of the demonstration. The destination directories will be these 4 that I highlight here. They are named to indicate the type of output they will capture. The first at the top here is land model -180 by 360 alone, and that's simply going to be the regridding to that grid of those files. The next example will do the very same regridding, but we'll only do it for selected variables. The last 2 examples we will do climatology and time series generation for the entire 1850 through 2014 span of years. So let's take a quick look at the actual scripts that we will be running. So if I scripts. There are 4 scripts. The first one, just the general regridding. The second one will do the selected variables. Then the climatology, and the time series will be the last. So let's take a look at these scripts. If you look in the guide on the left, you'll notice that examples are depicted with certain parameters for the runs. I've chosen to do something a little differently because I don't want to reuse the output directory. You'll see there's a reason for that. So let's go ahead and examine the first of these scripts. So in this very first example, we'll be taking only the year 1850, and each of its months will be regridded from the native grid, NE30 NP4, to 180 by 360 grid. We'll need the map file that conducts that the weighting between the 2 grids. For those of you who may not be familiar, the NE30 NP4 native grid is a cubed sphere grid, and to visualize that, imagine that the Earth was elastic and you grabbed it by its 8 corners and stretched it out into the shape of a cube, and then wrote or inscribed 30 lines on each face in both directions, so you end up with 900 little squares on each face, and then you let go of the corners and it snapped back onto the spherical Earth, and the images of those squares, a little bit compressed, of course, near the corners, becomes the grid, the native grid. And we'll be converting that to a 180 by 360, which is quite simply a latitude and longitude 1 degree units in each of the two directions, latitude and longitude. So it's a finer grid and a different shape, obviously. The input directories and output directories are exactly what we've already reviewed. We need to specify those. And in addition, unlike doing atmospheric regridding, land file is needed to indicate what's called the land fraction. And that is that unlike the atmosphere, which of course covers the entire globe, land exists in certain cells and not others, and some cells may only partially be land, partially ocean. And so that detail is accommodated by what's called the land file. So the command line will simply be the NC remap tool, followed by the parameters map file, input and output directory, and that land fraction value. Go ahead and close this, and we can actually just go ahead and run it. I think it runs rather quickly. Doing 2 months at a time, and only has 12 months to process, and so it's all done. We look at the output directory. Output directory is this one right here. So these are the this is a listing of the regridded output files. You'll notice that there's nothing in the name of the files to indicate that they've been regridded to 18360. In fact, the names are identical to the inputs. There's no renaming done. So if you were to do this in the same directory as the source, you would end up clobbering your source. There are other outputs that also are different, and yet they'll produce exactly the same name. I find that disturbing, and the reason why I'm very careful to make sure that my outputs end up in directories that describe what they are, and I make sure that the output goes into the appropriate directory. So now let's go on to the second example. This script is actually identical to the previous one with one exception. It specifies variables. Here are exactly 2 variables. It could be more. It needs to be a comma-separated list. Each variable must have both a time and a grid attribute. You can use NCDump to look at the -H to look at the metadata in a file and identify for each variable there whether it does or does not have a time component and a grid component. And so beyond that, we're using the same tool, NC remap. The parameters are effectively the same, with the one exception of the -V bars at the beginning. So we'll go ahead and run that script. You'll notice that this runs much faster, as it's only looking at regridding 2 of the variables, as opposed to what could be up to 100 or more in some of these models. So this is much faster. Once again, if I now look at the output, in fact, let's look at the output of the previous run. And then we'll also look at our most recent run, which went into this directory. You'll notice that they are identical. So you can't tell by just looking at the file names what you've got. and what it contains. However, I have another window open here. If we open it and look very quickly at those same two commands, I'll do a long listing this time, and you'll see that there is a very big difference between them. Here are the outputs from the first run, where we regridded all of the variables, and here is the output of the second run, in which we only selected two variables. The names are identical, but if you look at the sizes, it's very clear that these files are all 77 megabytes in size. These are just a little bit over 1 megabyte. So we've saved a great deal of space and runtime by regridding only the variables of interest. So minimize this. Now let's take a look at the third example. I'll scroll the guide here on the left. Actually, the example I'm going to be giving is a climatology, and it's not indicated here in this guide. So we'll just look at the script. This is the guide shows the fourth example. So let's go ahead and the parameters for a climatology or a time series, for that matter, are considerably more extensive than they are for the simple regridding. The map file is the same. Input and output directories are what you make of them. In this case, we're still looking at only two variables. But now we can choose a start and end year if we don't want to process all of the years. There are flags for compression, format and compression, per variable compression of the output. Very importantly, there's a model type here, land model 2. If it's not the default, which is the atmospheric model, and you leave that off, it'll complain that it can't find the atmosphere models and the files, and of course you don't have those if you're working with land, so you need to add that parameter. There is a special variable here called December mode. Ordinarily, our files are organized by year from January through December, but if the very first year begins in January, the modelers like to think of seasons as running from December, January, February, then March, April, May, etc. And so they expect for a file for data that begins in the year 1850, they expect December of 1849 to be present. If it's not, the tool will complain and exit. And so you have to override that by telling it that there is a December mode called seasonally discontinuous December, in which case it will ignore the fact that there is no initial December value for the first season. So you need also a case ID supplied as a parameter. That case ID is merely the name of each file up to the not including the realm and the year, month, day part that varies. It's just the part up to that point. We still have the land file to give the for a land fraction, and then the command line. In this case, the command line the tool we're using is NC-Climo, not NC-Remap. We'll use NC-Climo both for climatologies and for time series. They're very similar. And the command line simply consists of specifying each of the values that we've depicted here at the top as variables. So let's go ahead and run it. very long. It takes maybe about 30 seconds. There's you'll see that the output will be a history for each month of the year. That is a history of all the Januaries, all the Februaries. And then, having completed that, it will output a summary for each of the seasons: December, January, February, March, April, May, etc., and then an annual wrap-up. So it's completed. Took 31 seconds. It's didn't take that long. And so let's take a look at the output. That would be the Climo output directory here. Make sure we put it in one column. So you notice that it actually outputs 3 files for each type, for each month, for each season, and for the annual wrap-up. What it's doing here is it's conducting the climatology for each month to the Regridded output. It conducts the very same climatology on the original native grid, and that's what you see with the shorter name here. And then it creates a link here, a name that actually points to the longer one, the one that has the targeted regridding. And so maybe you can actually see that better if I just didn't type it to more and just do this. And you can see the color. The link is a link to the longer named output file. And we have, you can see from the names that we've gone from 1850 all the way through 2014. And but the years are, or the months, I'm sorry, are the 3rd month, 4th month, 5th month, 6th month, all the way through December. And then we have the August, oh, that's the annual, I'm sorry. December, January, February, the winter season. The March, April, May, spring, June, July, August for the fall, I guess, and then, or maybe I got them slightly shifted there, but September, October, November is the last season, and then we have an annual wrap-up. So that's the kind of output you'd expect from a climatology. Now, let's go ahead and look at our last example. That will be time series. And so here, the layout is very similar to the climatology, except for one very important difference, and that is this one flag. That's the years per file, and that indicates how many years to go by before we output a summary. So in this case, it's 50 years. So there'll be a summary each 50 years for each of the variables that are listed here. Other than that, all of the outputs are, all of the inputs, I'm sorry, are exactly what they were for the climatology, except there's no model that's necessary. It'll work for atmospheric, land, and ocean, and past ocean. So let's go ahead and run this. In this case, our output should look like one file for each type of variable that we're doing a time series, and one for every segment of 50 years. Except as you see here, it also says in one segment of like 15 years, because into the year 2000 and beyond, we've only got 15 years and not 50. Perhaps I should just pause this for a moment so you're not waiting.
This conference will now be recorded.
All right, so we finally completed. That took a little bit longer. That took 2 minutes and a half, roughly. Let's take a look at the output. That will be the destination land model regridded time series. And what you see here is that we have files for the first variable and separate files for the second variable. Each variable is output a range of 50 years at a time. So we've gone from 1850 to 1899 December, and then from 1900 January through 1949, etc. 50-year increments. And we also have both the time series onto the regridded map grid, and also the same time series for the original native grid. So we have both of these for each variable all the way through 2014. So that largely completes the examples. I think I'll just end by giving you my notes. So in case you want to copy any of these resources, you won't have to search backwards through the video to figure out where they appeared. And I'll leave this up for a few seconds, and then hope you enjoyed the tutorial. Thank you very much, and have a good night.